let me thank the organizers for the opportunity. Oh, okay, maybe you should. Yeah. So yeah, thanks for the opportunity to talk about my work. And so this is something I've been doing with Shinan and Vasco, and it's about computing 5-point correlation functions in supergravity. So let me start with some motivation why we want to do it. So there's several reasons, and first is that in a CFT, basically we always want to compute the set of dimensions, the spectrum, and the Opie coefficients. And there are several of these, so let me denote like this. So these guys would be, for example, the Opie coefficients of 3 protected operators. These would be of 2 protected operators and a non-protected, and 2 non-protected operators. And in supergravity so far, people have started to understand the dimensions and these protected Opie coefficients. And even these ones, so these ones are easily accessible if you do a 4-point function of, say, at x1, O20 prime at x4. So if you do an OPE here, you're able to go, you're basically going to extract here this kind of Opie coefficient where between 2 protected operators, the external ones, and possibly a non-protected one in the middle. And so what we are interested in is if we want to really understand the CFT, we have to go a bit further and, for example, also try to extract this kind of stuff of a coefficient of a protected operator with 2 non-protected. And a way to do this is basically by doing a 5-point function. Because in that case, once we take a double OPE, this becomes something like this. And here we have this C circle, circle dot. But here we have possibly the Opie coefficient between 1 protected and 2 non-protected. So it's only by considering the 5-point function that we can possibly access this kind of information. So that's why reason number 1, we are interested in doing this, so that we can take double OPE and extract this, or even we can do a single OPE and extract 4-point functions where one of the external operators is non-protected itself. So the second reason is that there was the work of Shinan and Rastelli, where they found that the Mellin representation for 4-point functions had a simple, basically had a simple structure. And so it's interesting to, well, one can wonder if maybe 5-point functions also have some sort of structure. And so we are starting, that's what we're starting with the first object we can compute, which is going to be this 5-point function of these 20 prime operators at strong coupling. And it's the first step, and once we can maybe go to other operators and start gathering some data, maybe we can start seeing some structure and understanding if there's a generic Mellin representation for this type of correlators. And finally, there was also this nice paper of Simon with his student last year or something like that, where they noticed this very interesting SO2,10 symmetry, where it looked like there was a conformal 10D symmetry in these ADS 5 cross S5 correlators. So it's interesting to wonder if is this going to show up at 5 points or even higher. And so in order to understand if this happens, we have to start dealing with these objects to see if maybe this enhanced symmetry really persists at higher points. So I think these are the main motivations. So now let me Sorry? Yeah, no, so you get the double trace and the double trace, yeah. Yeah, I think it's possible, yeah. And so, exactly, so we are doing this, so that's what I'm going to say next. So what's the setup? Okay. The setup is that we're going to consider, so let me describe this O20 operator. It's a function of x and y, because so this lives in the 0 to 0 representation of the SU4. And so we use these y vectors with this index going from 1 to 6 to encode the symmetric traceless representation. And yeah. This evaluated at x. And so these guys, so this is clearly symmetric, and we must require that y squared is 0 so that it's a symmetric traceless representation. And so what we are going to do is these operators are defined in n equals 4, and yeah, so this is in n equals 4, d equals 4. And so what we're going to consider is go to the ADS dual, and these have some these are dual to some scalar fields as I in basically type 2B Sugra in ADS 5 cross S5. And so what we're going to be doing basically, so this is large N and large Toft coupling. And so what we're going to be interesting is basically compute the amplitude no, yeah, so, okay, this is bad notation. So this labels the, okay, let me call it anything else. I prefer to change these ones, actually. So let me do like this. So this is index from 1 to 6, and 1 to 6. And this index I really labels the 20 degrees of freedom that are encoded in this representation, okay? So, yeah, 20. And, okay, so we want to compute the amplitude of 5 of these guys. That's what we're going to be doing. Okay, so this is the setup, and let's also think from the point of view of, let's kind of go back to n equals 4 to get some understanding of what can appear. So, so there are 22 R-symmetry structures that can appear. So these are things that would be like a pentagon and like this. So this would be I, J, K, L, M. And so this diagram would correspond to our symmetry polynomial of the form I, J square, J, K square, K, L square, L, M square, and Mi square. Okay? So there are 12 such terms. Right, and there are 10 of these, which basically correspond to the other only possibility, which is, if I write here I, J, K, L, M, this is I, J square, J, K square, K, I square, and L, M to the 4, okay? So these are the 22, so like in the 4-point functions, there were 6 terms. And these 6 terms, basically, there's a map of these 6 terms to the 6 representations that appear in the OP of 20 prime operators. And here it's the same, but there's 22 terms which map to the 22 representations that appear in this the double P of these 20 prime operators. Okay, so let me just, okay, so yeah, just notice, so this is polynomials of degree 2 in each yy. So if we look, so this is so this O20 is a protected operator with this R charge 2 and dimension 2, and so the conformal weights are 2. So if we write this correlation, let me write this correlation function G5 as is O20 x1 to O20 x5. Then basically we can write if we multiply this by something of this form, x1 2 to the 4, x3 4 to the 4, x 1 5 3 5 squared. This will become basically a function of cross ratios. So basically I'm cancelling the conformal weight of weight 2 at each of the points 1 to 5. And so this basically becomes my curly G, which is a function of 5 cross ratios, U1, V1, U2, say, V2, and some W. And so just to get an idea of what this is, so usually in the 4-point function we can use conformal symmetry to put one operator x1 at the origin, x3 at 1, and I'll send x5 to infinity, and so okay, so we can use conformal symmetry to do this, and we can basically then we have x2 is going to be somewhere on this plane, and there's going to be another point which is going to be somewhere else, and so there's going to be another plane, and which I don't really mean to be perpendicular, and the other point will be somewhere here, x4. So this will be something like somewhere on this point, okay? And so this distance, like the usual, we can relate this distance to U1, for example, and this to V1. And we can relate this distance to my U2. So I'm choosing these variables because it's going to be natural in terms of the double OPE. When I do the OPE 1, 2, and 3, 4, I'm going to be sending U1 to 0 and U2 to 0. So that's going to be my double OPEs when both U's become small. And so then there's going to be, so this x4 is going to be at a sort of distance V2 from the origin. And then basically this distance, it's getting a bit crowded there, so let me basically, so yeah, so this distance is 1, I send this point to infinity. So basically this x24 square is basically going to be my final fifth cross ratio. Okay, so this is the picture. Is this clear? Okay. Very good. So this is what we have. We have a function. So yeah, maybe let me just write here. So we're going to be taking, when we want to do an analysis, we're going to be taking an Euclidean OPE limit, in which basically we're going to be sending U to 0, and V1 to 1, U2 to 0, V2 to 1, and I think my definition of that W is going to basically be going to 1. Okay. So very good. So this is the setup. So we're going to be computing this 5-point function. It has this R symmetry structure. It's a function of 5 cross ratios that basically are in 2 planes. So I think now I'm ready to move on. So I'm going to basically be describing the several tools we're going to need to perform the computation. So let me first start with, so now let me talk about the tools. And the first one, let me, I guess, introduce Mellin space and factorization. So Melian space, let me just start by writing. So that basically this correlator G5 is basically going to be an integral over set of d delta ij. Some Melian amplitude that depends on these new variables, delta ij, x ij squared to the minus delta ij. And then we put here our gamma functions. And so in this case, so it's a 5-point function, so there are 15 delta ij's. Oh, sorry, no, that's 6 points. There's 10. And with the 5 conditions, which maybe I should write, which is sum of j different than I, delta ij, is to be equal to delta I. So it is just basically saying that this function is conformal weight delta I, which in our case is going to be 2 at each point. And so we have 5 conditions, which means that there is in the 5-point function 5 independent delta ij's. Okay? Very good. So it's also important, so this is just the usual. So now let me move one step further, and let me also introduce the Melian representation for operators with spin, or for correlators where one of the operator has spin. So in this case, I'm going to be considering some operator, some spin j, and let me say position x0, and then I'm going to have my other operators, O1, x1, OK, xk. And so what's going to be the Melian representation for this? It's going to be something of this form. Let me first say, so a useful way to encode the spin in these operators is by encode the tensors by polynomials. So I'm basically going to write these as oj z x0, or basically this is just z mu1 z mu j contracted with this operator which has spin j. Okay. So really, so this is the. So let me just write here z and x0. Okay, so what's the Melian representation in this case? We're going to have different structures. So we are going to have to sum over I1 to k. So we cannot construct this polarization vector with the point x0, that to be 0. So we have the k possibilities of contracting. Let me actually, I think for simplicity, I'll consider only the j equals 1 case, just so that formulas are a bit simpler, but everything is very similar for higher spin. So there is only one of these guys, one z, and so I can contract it with this x0i. And then I'm going to have an integral over these the delta ij. And so in this case, so let me write my delta ij and some delta I, where in this case I'm going to have a product over I less than j of gamma delta ij over x ij squared to the delta ij. So these I and j go from 1 to k. So these are only for these k operators. And then I have a product I from 1 to k of some delta I plus a Kronecker delta. Sorry. Let me call this A. And Kronecker delta I A. And this is just x0 I squared to the delta I plus Kronecker delta I A. Okay. So basically, so yeah, we just have k plus 1 operators. So this is my, so there's these different structures. So I'm summing over this index A, this polarization part here. And for each of them, I'll have a different component of the Mellin amplitude, MA, okay? So for example, in this case, there will be k components, except they're not all independent. And so let me just, so if we analyze this, we want to say that at each point, there's a correct conformal weight. So basically, we have that, so there's this delta I plus sum of delta ij should be equal to delta I. And if we analyze the other equation, so we see that if we look at the point x0, we see that we have sum of delta I is equal to, in this case, it's 1 minus the dimension delta of this guy, which maybe I should have specified. So this guy is a spin operator as dimension delta. So in general, let me just leave this form more generically to be j minus delta. So for a spin 2 operator, this would be 2 minus delta. Okay, so this is our Mellin amplitudes. So they do obey, there is a constraint. For example, for still, let me just specify for spin 1. There's this constraint that gamma I mi is equal to 0, sum over I. And this really just means a very simple thing, which is there's this work. Maybe I should say that this factorization work is by João, Vasco, and Emilio from 2014. And it's very easy. If you look at the paper of João, where they studied correlators with spin in embedding space, for 4 points, there's some structures. If we put one operator with spin, V in position 1, for example, it seems like there are 3 possible structures that you can write, and where this V1 ij is basically just this usual x1 I mu over x1 I square minus x1 j mu over x1 j square. Okay. But you can easily see that this obeys a very simple relation, which is v1 2 3 plus v1 3 4 minus v1 2 4 is equal to 0. And so this, the fact that you can express your correlator only, you can choose your basis to basically be just 2 of these structures, for example, v1 2 3 and v1 3 4, is basically what this is saying. That there is a relation between the, so for example, in this case, we'd have a 4-point function here of one operator with spin and 3 others. There would be appear to be 3 components for this Mellin amplitude, and all that this is saying is that they're not all independent. There's one degree of freedom killed, just like there's 1 degree of freedom killed by this equation. Okay. Okay. So these are the Mellin amplitudes, and finally, let me write the factorization formula, which states that this Mellin amplitude has to have a pole in some position, delta LR minus delta minus J plus 2M, and some residue here. So all is, we are looking here at Mellin amplitude with, that's like this. And this is saying that basically here at this, there's this delta LR, which is equal to the sum. So these legs 1 to k, k plus 1 to n. And so here this is sum of, say, a1 to k, and I k plus 1 to n of my delta ai. So this is equal to this delta LR. And so there is a pole. If in the OPE of these first k operators, we have an operator of dimension delta and spin j that appears, then we'll have a series of poles in the Mellin amplitude exactly at this location. this variable, which is a combination of our Mellin variables, exactly at this location of this twist delta minus j. And the interesting feature is that this residue qm basically is like the usual factorization formula in amplitude. So for example, if I focus for spin 0 and the first pole m equals to 0, this q0 is basically just proportional to the Mellin amplitude on the left with some variables delta AB times the Mellin amplitude on the right with some variables delta ij. Okay? So where the delta ij's are the variables in the right Mellin amplitude and these for the left Mellin amplitude. For example, for J1 and m equal to 0, you'd have that this the residue of the first pole would be something like gamma ai, m left a, delta ab, m right I, delta ij. Maybe let me use different notation here, so it's not confusing. Bj, b, sorry, a, b, c, okay, c, okay, okay. And so because we have an operator of spin 1 flowing, it means that we have to use this Mellin amplitude where there are different components, and we are here summing over the different components of the Mellin amplitude on the left and on the right. Okay. Very good. So this is factorization, and so this is one of the tools we're going to use. The second tool is the chiral algebra twist. So this means that this O20 prime is in the cohomology of a certain combination of Q's and S's, the supercharges in n equals 4. And this combination, let me call it A, commutes with a twisted translation into D. So what we do is we have to set all the points to be in the two-dimensional plane. So in 4 dimensions, that's where they are already. For 4 points, that's where they are already. For 5 points, we basically have to choose these planes to be in the same plane. And so clearly one of the cross ratios would be a linear combination, or not linear, a combination, or non-linear combination of the other. So really, we will have to put all 5 points in the same plane, and we would have 4 independent cross ratios. And so when we go to 2D, like you can label the positions. So since it's two-dimensional plane, there's anti-holomorphic and anti-holomorphic positions. And so if we choose, there is the twisted translation. Which commutes with that combination of supercharges, which means that once you do the twisted translation, so if you consider a correlation function, so that combination of charges annihilates this operator at the origin, and then if you consider correlation function of let me see, more generic, at other positions, x2, xn, where these operators were translated in the two-dimensional plane using this twisted translation that commutes with this combination of charges, then in this case, this correlator is holomorphic and does not depend on the coupling. Does not depend in one. Okay, so effectively what we do, we restrict to an SO4 part of the of the polarization vectors. So these, we said this T5 equals T6 equals to 0. So effectively we have this just T mu, which is the other 4 components in this SO4. We're restricting to an SO4, and then we're going to basically restrict when we translate the operators in this plane along this Z bar. We're going to have to also do a translation in a SU2 of this SO4, which would correspond. So now we have this SO4, which is the SU2 times SU2. So this basically, so remember that this guy was null. So really we can do like the usual spinnericity formalism. So this is just variable V alpha bar. And because they are on the plane. They are on the plane. They are on the 2-dimensional plane. Yeah, yeah. Restricted to R2. No, but I'm choosing specific O tilde operators, which are these twisted translated operators. So it's a specific choice. It's not any operator. It's like I'm taking this one, and besides translating it, I'm doing a translation in the SU2 of the SU4. No. This is a generic statement about the chiral algebra twist. And so we can restrict to an SO4. Almost we decompose into this spinnericity because it's null, and because it's also, we can rescale also. We can also rescale. We can set these VI's to 1, sorry. So these are 2-dimensional things, some coordinates, and this V bar to be some Y 1 and Y bar I. And what the chiral algebra twist has to require is that these coordinates, Y bar I, become the anti-holomorphic coordinate in the 2-dimensional plane. So this is what it means when we are doing the twisted translation, is that when we are moving the point to some Z bar coordinate, we have also to choose a specific position in this SU2 inside this SO4. And when this happens, whatever correlation function we consider is going to be holomorphic, so depend only on Z and Y, sorry. Yeah, well, let me call it alpha. Yeah. And so if we consider our 20 prime 5-point function, and we do a twist, we set this to be with this, sorry, let me call this alpha. Alpha bar I equals Z bar I. And so remember that this has to be now on the R2, so the 2-dimensional plane. This has to be a function of Z I and alpha I, which does not depend on the coupling. Okay? Very good. So this is the chiral algebra twist, and you can see how it's going to impose a very strong constraint on our correlator. We're going to have to be doing something with this 5-point function. We're going to impose this, and then this means that whatever we obtain, we're going to have to obtain this specific holomorphic function, which, because it does not depend on the coupling, has to be equal to the same function you'd obtain with free field theory. Okay? Very good. This is not as strong. So yeah, up to 4 points, it was equivalent to imposing the superconformal word identities, but at 5 points, it's not, but this is at the moment the best we know how to do. So yeah, it would be interesting to understand how to impose the full superconformal word identities, because that would in principle impose stronger constraints. We're able to fix almost everything, and then we can just do a simple double Opie analysis to fix the rest. But for example, maybe if we consider the full superconformal word identities, maybe everything would be fixed up to a single overall factor. So that would be better, especially because then in the future, if we try these with higher weights, the superconformal word identity might be better at fixing everything, rather than if we do higher weights, and then we're going to have always a few undetermined coefficients that we'll always have to do double OP to fix. So that's a bit annoying. So in principle, it would be better to be able to do. It will relate the coefficients between these. I mean, there's going to be a lot of things besides the 22 different structures. There's going to be, for example, in Mellin space, there's going to be the double poles and related to double exchanges. There's going to be regular part, and in fact it's going to kind of constrain everything at the same time and relate probably coefficients that appear in the regular part with things that appear in. I mean, it's even simpler than 22. In fact, there's really only 2 independent functions because there's a permutation symmetry of the 5 points. So we know, so there's 22 structures, but we know that if you permute 2 points, it has to be the same. So there's, so it has to be invariant under all the permutations. So really there's one undetermined thing times those pentagons, kinda, and then there's like one undetermined coefficient for all the triangle with the lines. Yeah, there's 6. No, but for example, for the 4-point function already, by imposing basically just crossing symmetry, you could relate these 6 functions to only 2 of them. And then once you impose superconformal symmetry, you relate these leftover 2, and it's exactly the same. In fact, for the 4-point function, you had the squares and the 2 double lines, and so there's 3 functions here: so A1. A2, A3, B1, B2, B3. And crossing symmetry, which just means like permuting the points, basically relates these to a single function, A, and these to a single function, B. And then once you use supersymmetry, you can relate them. Supersymmetry. And here, so what I'm saying is that there aren't like everything. We have the same, so we have these 2 different structures, so we can relate the coefficients in front of each to a single function, and then in principle you have to impose constraints on to relate these functions. Yeah. Okay, so finally, let me just make a small note. The third ingredient that we'll need, because we're going to be using factorization, we're going to have to be able to compute also. Because once we impose factorization, we're going to have that these will have to basically be able to do this 3-point amplitude times 3-point amplitude. That's okay because this is known, but there's some things that are not so well known, which is the contribution of this R symmetry current and the stress tensor. So this part, the 3-point function, is okay. However, these 2 4-point functions weren't yet known. So what we had to do is that this works well for 4-point functions. We have this kind of, so they all belong to the same supermultiplet. So we have the supermultiplet, so there's the coordinate x. Yeah. At large lambda, there's a lot of operators that decouple. Is that what you mean? Yeah. And yeah, even further, because we're considering only 20 prime operators, there's this truncation, consistent truncation to the 5D gauge supergravity, n equals 8 supergravity. So you really know that there's only these 3 fields. If you compute Witten diagrams, there's only the scalar, the graviphoton, and the graviton in the exchanges. Yeah. Yeah. The fact that I'm going to need these correlators in specific is the first time where I'm considering that. Yeah. So when we consider the factorization, so we're going to consider the Mellin factorization. So we're going to be looking at the poles, and the poles in the exchange diagrams. Yeah, it is a bit sketchy because it looks a bit like the from n equals 4, but yeah, really, it's related to his question. So we have to think that here we are already at large lambda. So really, when we do the exchange diagrams, there's only 3 fields appearing there. And when we do the factorization, it's going to be on the left malin and right malin for those 3 fields, which are going to be the duals to these O, J, and T mu nu. Okay. Thanks for the clarification. So the thing is that we have these, basically they all belong to the stress tensor multiplet. And so we can write them with these theta variables, because it's a half BPS multiplet. This means that really we can write this with some reduced number only. So these are 8 plus 8 thetas, but we really can express things with 4 thetas and 4 theta bars. And 4 and 4, which means that a 4-point function, so this is very sketchy, but the 4-point function roughly will have 4 plus 4, 8 times 4, which is 32 thetas, okay? And this is exactly the same number of Q's and S's in n equals 4, which means that you can really use the supersymmetry to write this basically all these components in this and relate all these components of this multiplet in the 4-point function. And by doing that, so we took these results of paper of Belitsky, Korchemsky, and other people from 2014. We used these ideas that basically they have the results there. We just had to play a bit with them, manipulate them a bit, and we were able to obtain these 2 guys that we needed. Okay? So finally, we can move on. So I think I've introduced all the tools. So what we have to use, we're going to have to understand this Mellin amplitude, also for operators with spin. We have to be aware that there is factorization at the poles of this 5-point Mellin amplitude. And finally, there's also, it's going to be very important to use this chiral algebra twisting. And in order to use factorization, it was important that we were able to obtain these 4-point functions. Okay, so now let's move on to the fixing the 5-point function. Okay, so now let's start drawing some diagrams. So we have a first method. Method number 1 was basically this position space method that already Sheenan used for 4-point functions in 60, 2,0, and then equals 4. So position space method, where basically what we do is we compute Witten diagrams, but don't worry about extracting the couplings. So this is what Aritunov and Frolov did like 20 years ago, and it was their famous many pages long extracting, for example, the quartic vertices. It was a lot of work. So basically, it's like we don't look at any of that. We just write the Witten diagrams. So let's see what appears in this case. So there's, maybe I'll just draw. So there's double exchange diagrams, single exchange diagrams, and also the quintic contact diagram. So let me start with the double exchanges. So we can have here, so these normal lines will be my scalar operators. So this is a double exchange where you have the scalar as exchanged in both times. So then there will be also this double exchange where we have this dashed line, which will be my graviphoton, so the dual guy to this J mu. And in fact, our symmetry is compatible with having the exchange of 2 dashed lines, so 2 J mu's, because this is basically a 15. Oh, maybe I should mention that. So this O is in the 0 to 0, This J is in the 1, 0, 1, and T is in the 0, 0, 0. So it's T is a singlet of the R charge. This guy is just in this antisymmetric, and the other one is our original guy. So this is a 15, 15, 20, and this is allowed by our symmetry. So that's good. So the other diagram we have is basically we can have a scalar exchange, and then we can have a graviton, which I'll denote by this curvy line. And I think that's it. Because we cannot have another graviton because that would be singlet, singlet, 20, which you cannot form a singlet out of those three representations. So next, we have the single exchange diagrams. So we have a single exchange of the scalar, and then we have a quartic interaction for the scalars. And we have the dashed line, which is our J mu nu, coupled to three scalars. So this doesn't really appear in the papers of Aritunov and Frolov because they didn't need this type of vertices, so they kind of omitted it. But if you dig up to the real, the 5D gauge, the supergravity, you can see these type of things. And finally, we have the graviton coupled to three scalars. And at last, so these are the double exchanges, single exchanges, and finally we have our star, the quintic diagram. So everything here will basically contribute, let me call it G5 singular, because all of them have exchanges, which means that these will appear as poles in the Mellin amplitude. So this will contribute to the singular part of the Mellin amplitude, while this will be my G5 regular. This will basically just be a D2, 2, 2, 2, with 5 twos. And yeah, so that's regular, no pole in the Mellin amplitude. So I can erase that one. Okay, so I don't have much time, and it's a bit technical, but maybe let me just mention how we can, for example, by using factorization, fix a lot of or relate a lot of the couplings. This is just, I'm only doing the 20 prime, so only the dimension 2 operator. Yeah. I'm not sure I understood, but yeah. Yeah. So yeah. I was being a bit. Yeah, it's true. Yeah, I was actually going to mention that. Okay, so let me. 12 minutes. Okay. Let me try to just sketch, for example, how we do if we look at factorization for the scalar, because that really gives a lot of constraints. So factorization means that we have like this 3-point amplitude and a 4-point amplitude. And what contributes to this? So in this case, it's this double exchange. So let me now start putting points 1, 2, 1, 2, scalar. So here, let me put, for example, 0.5, and we have to do permutations, because it could be, the guy here could be 3 or 4 as well. And we have also this diagram. Oh my god, my balls are too small. That sounds weird. So here it's the dashed line, so it's the graviphoton. So here I have points 1, 2, and 0.5. We also permutations. Plus now a big ball, 1, 2, and the graviton, plus permutations. And finally, let me add just the single exchange. And here, okay, here there's also several possible terms. So here, let me put these twice, because we can add some derivatives here in some of this quartic interaction. And so we can at most add two derivatives because this is a two-derivative theory, and also because of the flat space limit. And so in this case, there's also permutations of where the where the derivatives sit. Okay. And so each of them will come with a coupling, which you could in principle extract from looking at the effective Lagrangian of the theory. So here this is going to be, let me just call it like some lambda s. And so these guys are just given by the same coupling, but with a permutation of the points. So SS. This coupling I'll call SV. And here the vector and the graviton, sorry, the scalar and the graviton. And here I have some scalar coupling with just a zero derivative, which I'll denote like this. And also I'll add an index I. And here I have some scalar and two derivative and index I. So let me explain what this is, because I'm kind of omitting this kind of sketchy, but what I mean with this index is that here really there is only one R-charge polynomial, because here we have the scalar, so this is basically, you can project into that those representations, and there's a single polynomial that corresponds to this. So there's a single R-charge polynomial, and it will appear in these permutations. Here there's also a single R-charge polynomial in all these cases. What happens here is that here we're only imposing that there is the 0 to 0 representation in the 1-2 channel, which means that when you look at all 22 polynomials, and you, for example, well, you really can project into the 0 to 0 channel here, there's a basis of 6 polynomials left, which basically encodes the 6 representations you could still have if you did the 3-4 Opie decompositions. So really here there's some polynomials Ri with I 1 to 6, and for each of them we have to put a different coupling. And the same here, because it's exactly the same diagram, so this applies for this and for that. So is that clear? So in this case, it's because we really have specific representations in 1, 2, and 3, 4 channels. There's a single R-charge polynomial. Here, because we only have a single propagator, it's kind of like there's some freedom in what polynomials can appear. So really, there's a lot of couplings here. There's 1, 2, 3, plus like 6 plus 6. And what happens is that there's a lot of technical work you have to do. So you basically have to compute these Witten diagrams, but there's techniques to write all of these Witten diagrams in terms of D functions, delta 1, delta 2, delta 3, delta 4, delta 5. And so we can write everything, all of these in terms of D functions with all these different couplings that are unfixed. And once we do that, then we have the functions. You can also go from position space to Mellin space. You can go to Mellin space for this specific combination of diagrams. And what we know is that this has to, the pole here in this basically like delta 1, 2, has to factorize. The residue here has to be the Mellin amplitude for these 3 amplitude times the 4 amplitude. And this is the things that we computed. So we computed these in position space, but then we wrote them in Mellin space, which means that once we go to Mellin space and we look at what's the residue of this couple, we can fix everything up to overall scale. Overall scale. It's really just factorization. Yeah. The fact that you write all these functions with all these different couplings, and then you look at the residue and you equate it to what the residue should be, which is the 3 Mellin amplitude times the 4, and you can fix everything up to the overall scale. And the conclusion is that if you look, so this was just an example for the factorization. Yeah. So yeah. no, 1 over n cube, in fact. These diagrams are 1 over n cube. Okay, no, yeah. If you worked really carefully with normalizations, we didn't even bother with working very carefully with the normalizations here. So we didn't even bother with fixing the overall. It's true. If you were very careful with the normalizations there, you could fix the overall coefficient too. It's correct. Absolutely correct. Yeah, we're going to use the Carroll algebra also later. Yeah, well, that's also why we are not being careful. But yeah, we're going to get there. There's a lot of reasons why we didn't have to be very careful with normalizations. And so the conclusion is that basically our G5 becomes this, there's an overall lambda singular scale times our G5 singular. And then we have to do our G5 regular. So here what we did was basically consider the possible quintic. There's 2 types of diagrams. There's this where just basically s I to the 5. But here we can put some derivatives. So basically there will be the quintic coupling with 2 derivatives. And so you can write all of these once again in D functions. And then what we did was impose the chiral. So we looked at, so once we wrote everything in terms of the functions, we took our full D5, imposed chiral algebra twist, or just perform the twist and impose that it has to be holomorphic and independent of the coupling. And what we obtained was that this G5 was basically still that scale, G5 singular, plus a single regular coefficient times D2 times a combination of those pentagons, which let me just write. So these are the R-charge structures. So it's a combination of these pentagons minus a sum over the triangle times double line. So this is the R-charge structure. It just happens that this specific combination of R-charge polynomials vanishes upon twisting. Okay, so this vanishes upon twisting, and so that's why we cannot fix it. So overall, we had this scale here because we didn't bother with normalizations, and then we had this number here in terms of this D222. Okay, and so finally, whoops. So what did we do? So basically, this is already pretty good. So we only use factorization and fix basically everything in the singular part, and then we use the Carroll algebra twist to fix the regular part up to a single coefficient. What we did next is basically we performed the double Opie analysis. And what happens is, for example, if we look at the channel, let me write, okay, 0 to 0, 0 to 0, for example, at the dimension 2 and 2, you should obtain basically the product of Opie coefficients for these. So basically, it's the C2 to the cube, basically. These operators are protected and have protected Opie coefficients, so that's why there's no subleading terms in these Opie coefficients. So we know this from free field theory. It's basically just the 2 square root of 2 C I1, I2, I3. So basically, by comparing these with our G5 upstairs, basically we fix easily that overall part in the exchange. And the second thing we do is we look at this 202 channel, and 40 seconds. With dimension 4 and dimension 4. What are these operators? These operators are in fact quarter BPS operators. which are protected, and furthermore have protected OP coefficients with themselves and with the half BPS operators. So we went and we did a free field theory computation, obtained those OP coefficients between 20 prime and these 202, which is in the 84 representation. So basically what we have 20, 20, 20, 20, 20. So we computed all these OP coefficients, which are all protected. So we computed them with free field theory. And then we compared with the OP analysis of our G5. And in that way, we were able to fix the other only coefficient, which I called lambda reg. So in that way, we use factorization, twisting, and a very simple OP analysis, and we were able to fix the complete 5-loop correlator. And I'm at 0. Well, I guess I can have time to do a few comments. So this was our first method. There was also a second method, method 2, which is we started from a Mellin ansatz. And so what did we do there? We just said, okay, we know what poles should appear, what double poles, what single poles, and what are the degrees in the polynomials. And then basically that's all we did. We wrote an ansatz, right, ansatz. And then we perform twisting. And the conclusion was that basically it fixed everything up to 3 coefficients. So 2 of these are the same 2 that were here, the overall in the single part and the one in the regular. The third one was a coefficient that appeared in a single exchange, but it appeared in a single exchange in the 84 representation. And so we know that the 84 representation cannot appear in an exchange diagram, so we could easily set it to 0. So this method was also very efficient. It just gave an extra degree of freedom, which was we didn't even have to do OP analysis to fix it. It was really enough to have just suppose that there's no 84 field in the exchange within diagrams. And finally, so I guess that's what I wanted to say, a bit shortened in the last part. And so what are the conclusions is that this worked pretty well. We're pretty happy. And there's a lot of things we can do after this. Basically, we can start trying to do higher weights. So for example, if we do, especially if we do at the same level of extremality. So if we do the 2, 2, 2 PP, this is at the same level of same extremality. Which means that in principle this should be almost as easy to compute. In terms of the Mellin ansatz, this just has in principle shifted poles. And so we believe it would be quite straightforward to do this calculation as well. And so that's one thing we can do. In the future we can also try higher weights in general. And that should be a little bit more difficult because the Mellin ansatz in that case will start growing. There will be more positions for the poles. So there is a bigger chance that there will be more and more undetermined coefficients. So we'll see how we can do with that. Another thing we can do after is maybe start looking at 6-point functions. Because the methods we used were pretty good. It worked pretty well. There is a difficulty, which is that in this part, where was it? Here. So when we obtain this, so if we wanted to do the same for 6 points, we would want to use factorization. So we would need to obtain the 5-point functions where we substitute a no with a higher current. And that's not obviously so easy, just from the fact that no one wrote a paper doing that yet. So we would have to work harder. And it's because the symmetry, in that case, there would be more thetas than supercharges, so it's not obvious that's very easy to do this for 6 points. But certainly it's a very interesting way forward to see if you can do more. And I think, yeah, that's it. So my time is over, and that's my work, and that's my conclusion.